Alright, welcome to the Chapter 9 Homework 1 review. This is the last material that we'll be responsible for on the exam that starts today. The average on this assignment was 9.68 out of 12, so a little bit higher than we have been, which is good to see that we're picking things up here at the end of the semester. And what I'll go over today are just some of the questions we had some difficulty with. This shouldn't take too long because these are all pretty basic conceptual questions, not a lot of depth, not a lot of steps to solving these problems. But we'll go through some of the ones, and as always, any additional questions you have, I'd be happy to address separately in person or over email. So the first one deals with atomic solids, and it's a true-false question. And anytime the success rate in a true-false question is less than 50%, it suggests there's some sort of misconception floating around. So this one is that atomic solids generally have low melting points. So we learned about different categories of solids, and we have, so the one that this is talking about is atomic solids. Within atomic solids, you have two different categories. You have metallic solids, and then you also have what are called network atomic solids. So atomic solids, as the name suggests, they're solids that only have one type of atom in them, so they're not compounds, they're elements. And then within these, again, there's two separate categories, metallic and network atomic. And metallic solids would be basically any metal, as the name implies. Again, not too difficult to learn there. Network atomic solids, there's a few of these nonmetals that fall into this category, and the two major ones are carbon and silicon that we'll be responsible for knowing. Carbon having two forms, both graphite and diamond, which are both considered atomic solids, and then silicon, which has the same structure as diamond but with silicon instead of carbon. So those are the two types of atomic solids, and both of these have moderate to high melting points. And the reason being that you have very strong forces that are holding the atoms together. So in metallic solids, you have metallic bonds, which are those delocalized electrons that float around and hold all the nuclei together. And those, it's relatively easy to melt metals compared to other types of solids, but still they have moderately high melting points. You don't typically have metals with really low melting points. And then for network atomic solids, they tend to have very high melting points because in those cases you have covalent bonds holding all the atoms together, and covalent bonds are very strong, so in order to melt the solid, you'd have to break some or all of those covalent bonds. So both of these are characterized by moderate to high melting points. If you're talking about something that would have low melting points, typically the only category of solids that have low melting points are the molecular solids. So we know that a lot of covalent molecular compounds exist as liquids at room temperature or even gases. So molecular solids tend to have low melting points because in this case you only have relatively weak intermolecular forces, either dipole-dipole forces, or in some cases, or in many cases, just London dispersion forces holding them together. But atomic solids, and which include metallic and network solids, both have relatively strong forces, relatively high melting points. So this one would be false. Okay, they're not characterized by low melting points. It's typically only molecular solids that are characterized as having low melting points. The next couple here deal with how we count atoms in these different cubic unit cells. So we have, in this case, we're looking for the equation that represents the number of atoms in a primitive cubic unit cell. So what we have to remember, first of all, are the different positions that we can have atoms located. So we have corners, we have, let's do this in order, or at least in a more logical order. We have corners, edges, faces, and then centers, or body centers. And so when you have an atom in the corner of a cubic unit cell, we count it as 1/8, meaning that you have that corner shared by 8 other unit cells, so the atom only counts as 1/8. Edges are shared by 4 unit cells, we count those as 1/4. Faces are shared by 2, so we count them as 1/2. Centers are shared by nothing, so we count them as a full atom if they're in the center of the unit cell or any position inside the unit cell. So with this in mind, we have these different positions that can be occupied in different cubic unit cells, and so each atom that's at one of those positions counts as it's shown here. And then in this case, what we're talking about is primitive cubic. So the second part of this is to not only know how we count the atoms, but to know in a different unit cells which ones of those positions are occupied. So in a primitive cubic unit cell, we have all corners are occupied in the cubic cell, but nothing else. So if we think about a cube, or some approximation of a cube as I've drawn, in a primitive cubic cell you're just filling the 8 corners. So there are 8 corners in any cube, and in a primitive cubic all 8 of those are filled. So if we want to count the number of atoms, we just have 8 corners, and each counts as an 8th. Or I guess the way it's written here is just the 1/8 is first multiplied by an 8th. But that would be the correct answer then, is A, because in a primitive cubic cell we only have the corner positions occupied. So it's just those 8 corners that we would count, which is a total of 1 if you want to work it out numerically. So that's how we do it for primitive cubic. The next one is body-centered cubic, which same counting rules: 1/8 for corner, 1/4 for edges, 1/2 for faces, 1 for the center. But in this case, we have a different type of unit cell. So in a primitive cubic, we had just the corners occupied, as we saw before. In a body-centered cubic, we also have 1 right in the middle. So as I said, in a primitive cubic, it's just the 8 corners that we counted last time in the last problem. And then in a body-centered cube, it's a little bit hard to draw this three-dimensionally, but you have one, which I'll draw in red, right in the center of the cube as well. So it's bounded by the 8 corners in equal distance, but it's right in the middle of the cube. It's not touching any of the sides, not touching any of the edges. So in a body-centered cubic structure, then, the number of atoms, you have the 8 corners, which count as an 8th each, so those are the corners, plus you have 1 in the body center, which doesn't get shared. So that would come out to 2, so the correct way to count that would be choice C. So this would be wrong because those are the faces. This one also includes faces. So for a body center, it's just the center and the corners. So we have 3 types of unit cells. We want to learn how to count atoms in all 3 of those types. It is a factor of knowing how many each position is shared by, and then which positions are actually occupied in the different types of cells. Next question here, we're kind of jumping around a little bit. I didn't really put these in necessarily any logical order. We're dealing again with atomic solids, and here the lattice points are occupied by group 8 atoms. So remember, group 8 is the noble gases. So that's going to be helium, neon, argon, xenon, krypton. So we're talking about a solid formed of these elements. Now we know that these are called noble gases, which means under standard conditions at room temperature, they exist as gases. But if we cool them down low enough, they would go into the solid phase at some temperature. And here, so if we have an atomic solids made up of these elements, we want to know how the atoms are held together. So anytime you just have a monatomic element, here we're asking what kind of forces are holding together, monatomic element or nonpolar molecule. So in both of these categories, the only forces of interaction between the atoms are going to be the London dispersion forces. So in this question, the correct answer would be London dispersion or some combination of London and dispersion. They're kind of used interchangeably. Either they're called London dispersion forces or sometimes just London forces or just dispersion forces. But any combination of these 2 words would have been what you want to fill in that blank with. And so when we have noble gases, those are the only types of forces that exist if you just have a monoatomic substance. And there's not going to be covalent bonds between these. You're not going to, when you cool these down, get any sort of covalent bonding because they're noble gases. They don't tend to form bonds. So it's only going to be London dispersion forces that hold them together. Alright, so that was another conceptual question about atomic solids. And then finally, the last one is, again, about types of solids. Most metals occur as ionic solids. And this one, again, is a true-false question where we got less than 50%, so clearly there's some things floating around. And what we should recognize is the different types of solids, so we can kind of revisit this again. So we have a bunch of different categories of solids. We have atomic solids, which include metallic solids and network atomic solids. We saw that on the first question, that concept. We also have ionic solids, we have molecular solids, and we have network covalent. Solids. So these are the major categories of solids that we have. We talked about the structures of many of these. And so when you have atomic solids with, again, either metallic or network atomic, as we said, these are what metals typically are classified as. So most metals exist as metallic solids. The only metal that's not a solid is mercury. All the rest, when you're talking about either main group metals like sodium, potassium, calcium, or the transition elements, iron, cobalt, whatever, name your favorite transition element, all of those metals on the periodic table typically occur as metallic solids. So this question would be false because metals tend to occur as metallic solids, as the name suggests. Network atomic solids, as we said, is just carbon and silicon. And then if we're talking about ionic solids, which is what this question is dealing with, remember that ionic solids, just like any ionic compound, includes a metal and a non-metal together. So it is true that ionic solids have metals in them, but they're not just pure metals, they're a metal mixed with a non-metal. So for binary ionic compounds, things like sodium chloride, calcium oxide, and so on, or you can have polyatomic anions in there as well. So an ionic solid is just the solid form of an ionic compound, which is how most ionic compounds exist when they're not dissolved in solution. And then you have molecular solids, which would be most covalent compounds. Or diatomic elements, or I guess I should say more generally, polyatomic elements. So things like water, ammonia, and all those would form molecular solids in the solid phase. Polyatomic elements, the ones that are solids at room temperature anyway, would be like I2, P4, S8. So these are discrete molecules that have that many atoms in them, and they're held together by just dispersion forces. So those are molecular solids. They're typically covalent compounds. And then finally, network covalent compounds. They are also covalent compounds, so they include two or more nonmetals. And we just have to recognize which ones are network covalent solids. And really, the classic example that we'll expect you to know is SiO2. So it's a covalent compound. It has silicon and oxygen, silicon being a metalloid, I suppose, technically, but more of a nonmetal, and oxygen also a nonmetal. And this, instead of forming discrete SiO2 molecules, as we talked about in class, this forms these large networks. But anyway, that wasn't too pertinent for this question. We're just trying to be complete in our categorization. But this question dealt with how metals, what type of solids metals form, and those would be metallic solids. So to make this statement true, you have to change ionic to metallic. Alright, so that's how we categorize different solids, and we'll get sort of another review of that in the last day of class as we kind of tie all of this together. Alright, now we're back to cubic crystal structures for the next couple. Here we're talking about number of nearest neighbors. So in this case, if a metal crystallizes in a primitive cubic lattice, each metal atom has how many nearest neighbors of the same kind? So when we're talking about number of nearest neighbors, the other term we use for that is coordination number. So these are used interchangeably, they mean the same thing. And essentially it's the number of other atoms that an atom is touching in a crystal structure. So in a metallic solid, or in if you want to know what the coordination number or the number of nearest neighbors, it's the number of other atoms that are touching that one or that it's surrounded by. So here we're talking about a primitive cubic lattice, and as we said, if we just draw one unit cell for this, in a primitive cubic you just have atoms at every single corner, so a pretty simple structure. But in this case we want to know what are the number of nearest neighbors. We can't just consider a single unit cell. If we want to know that, we have to actually extend this out in all the directions to see how many neighboring atoms does each one have, if you look at one of these atoms in each of the corners. So the way to think about this one is to actually think about the layers that are used to form these structures. So in a primitive cubic, the layers are sort of these eclipsed, stacked layers like this. So if we look at an atom in this layer, let's say this one here, we can see that in the same layer it has 4 nearest neighbors, 4 that are surrounding it. And then as we stack this layer, it's also going to have one above and one below that are equally the same distance from it. And so what that means, this hopefully helps you understand this number a little bit, but if you just want to memorize it, the number of nearest neighbors in a primitive cubic is going to be 6. So a primitive cubic lattice, you'll have 6 nearest neighbors for every atom in the structure. So that's going to be that answer there. Because again, there's 4 in the same layer, 1 above, 1 below, that make a total of 6. So that's how I do it for primitive cubic. In this case, we're talking about face-centered cubic, which is, in some sense, the most complex crystal structure we have. So in face-centered cubic, the positions that we occupy, and we didn't do the counting for this, but you should be able to, the positions that we occupy in a face-centered cubic lattice are all corners again. So all the cubic lattices have every corner filled. There's no cubic crystal structure that doesn't involve, at minimum, filling all the corners. And then we also have, as the name suggests, one in each center of the face. So each square face of the unit cell has an atom right in the middle of it. So a total of 6 faces that are filled. And so that's what the face-centered cubic lattice looks like. All of these are equivalent. I'm showing them in blue and red to distinguish the corners from the faces, but in reality they're all the same atom, and we're talking about an atomic structure like a metal. So all the same atoms, I'm just drawing them in different colors to keep them straight. When you again want to know, each metal atom has how many nearest neighbor atoms of the same kind. Now again, it's pretty difficult to do this from just a single unit cell by itself, because this doesn't show as much as we need to see. Because if we want to know how many nearest neighbors does any one of these atoms have, we have to extend the structure out. And I still think the easier way to rationalize this is to think about the layers that are forming these. So in a face-centered cubic, this is what we call cubic close packing. The layers look a little bit different than the last one. So we start with a row of atoms, and then the second row is going to be sort of in between the first one, sort of staggered from it. And then the third row is going to be still staggered from that. So the layers in a face-centered cubic structure have a little bit different of an appearance. And then if we focus in on this atom here and figure out how many nearest neighbors it has, this one is going to be surrounded by six that are in the same layer. But then if we think about the layers that are above and below it, what we have is this one is going to sit in sort of the crevice of 3 others. So it's going to be, let's see if I can draw this right. There's going to be a layer above that sort of fits like this. So there's going to be 3 above in the next layer above, and then also 3 below in the next layer below. So it's a little bit harder to visualize for this. There's some pictures in the notes that it might be a little bit better and help you understand this more. But again, if you just want to remember what it is, if you have, in this case, a face-centered cubic lattice, you're going to have 12 nearest neighbors, or a coordination number of 12. And that's the highest that we have. So this is the one, again, with the most efficient packing. So whether you're talking about, whoops, that should be neighbors, not nearest twice. So if you're talking about the face-centered cubic or the hexagonal close pack, which are both formed from these same types of layers. In both cases, you have 12 nearest neighbors, 12 atoms surrounding each one for the maximum efficiency packing. Alright, and then next one here again deals with the distance along any edge of a primitive cubic cell. Now some of these get pretty complicated, but for primitive cubic cells, the picture is quite simple. So what we're looking for is, in a cubic unit cell of any type, remember the geometric definition of a cube is that it's all sides are the same length, all 90-degree angles. And so what we're looking for here is what's the distance along one of these sides, which we abbreviate as A. Okay? Now again, there's some more complicated expressions that come into play when we're talking about body-centered and face-centered cubic, and we learn those in class, but I don't think we would expect you to memorize all of those. But for a primitive cubic, it's a pretty simple picture. And so what we look at is, if we look at a single face of a primitive cubic, remember that in primitive cubic we have atoms in all of these corners. Now typically we draw them with sort of spaces in between to help us visualize them better, but in reality these atoms are as close to each other as possible. So if we look at a single face, what we have is atoms that sort of fit each corner and sort of fill the whole face like this. So these are the different corner positions, and so as we go across one side length A, we have the radius for one atom plus the radius for another, so that means this A would be equal to 2r. So I think this was a multiple choice question, but you would pick the answer where the side length A in a primitive cubic is 2r. For other ones, it's more complicated what the relationship is. We had, radical 2r, 2 radical 2r, things like that, for the different ones that came from the diagonal. And we're not going to have you memorize all of those, but for the primitive cubic, it's a very simple picture, and we should recognize that the length along one side is just 2 times the atomic radius of whatever atom is making up that structure. Alright, and then finally the last one here, we're looking for which of the following liquids has the greatest viscosity. So viscosity is resistance to flow, and it's one of those properties that also depends on the intermolecular forces. So the stronger the intermolecular forces that you have in a substance, you have higher viscosity. So this is a property of liquids again. It's how thick the liquid is, if you want to think about it that way. And if we're trying to predict which liquid of these choices has the highest viscosity, we want to have the one that has the strongest intermolecular forces. Sorry, I keep changing my mind to write this. Higher viscosity. So stronger IMS correlates with higher viscosity. So we want to think about what are the intermolecular forces that are present in all of these. Keeping in mind that there are 3 major types of IMFs. We have London dispersion forces, which are the weakest. We have dipole-dipole, which is sort of next. And then we have hydrogen bonds, which is the strongest intermolecular force. Hydrogen bonds are just a special type of dipole-dipole forces that's especially strong. And so let's look at all these substances and figure out which of these intermolecular forces are in play. So for hexane C9HW1, anytime we have a hydrocarbon, which is just carbon and hydrogen in the formula, all hydrocarbons are nonpolar. So without drawing out the whole structure, it should be fairly clear just from the formula in this case that anytime it's just carbon and hydrogen, it's going to be nonpolar, and that's something you can hold as being true across all these different types of problems. So when it's a nonpolar substance, the only intermolecular force is London dispersion forces. So that's the only intermolecular force present in hexane. Now for the rest of these, if we have B and C, it's not obvious what these look like, but if we draw the structure here for choice B, it looks something like this. And if we fill in the lone pairs, which aren't explicitly shown in the formula, we have 2 lone pairs on oxygen. So this one is going to be, if we focus as oxygen as our central atom, it's going to be AX2E2, which is bent, and which means it's going to be polar. So we have oxygen in the formula, so we have polar carbon-oxygen bonds. Each carbon-oxygen bond is polar. It's a bent structure just like water, and so you have net polarity. So this is polar, so it's going to have dipole-dipole forces as well. However, it does not have hydrogen bonds, because in order to have hydrogen bonds, you need to have hydrogen bonded directly to oxygen. This one, all the hydrogens are bonded to carbon. So it's a polar molecule, but there's no OH bonds, so you're not going to have hydrogen bonding in this one. Choice C is almost identical to the one above. It just has one additional carbon atom in it. So again, it's still going to be polar, and it's still going to have dipole-dipole forces. So choices B and C have dipole-dipole forces. But then if we look at D and E, this one has clearly an OH bond. So without even drawing out the whole structure, we know that this is going to have hydrogen bonding. And then if we look at choice E, this has two OH bonds. So it's also going to have hydrogen bonds, but it's going to have twice as many because there's now two OH groups that can all hydrogen bond with each other. So the ones that have the strongest intermolecular forces are D and E. E has more of those intermolecular forces possible, more possible hydrogen bonding sites, and so choice E is going to be the one that has the strongest intermolecular forces, meaning we expect that it has the highest viscosity. Alright, so that takes us to the end of the ones I wanted to go over this week. As I said, a little bit quicker this time, all conceptual questions. Any more, again, all of these types of topics that we went over today are fair game for the exam this week. So if you have anything else you'd like to clarify before you take your exam, please come find me or please send me an email. Alright, I'll see you later today in class, and we have perhaps one more of these homework reviews before we close out the semester.